Okay, let's dive right into this. I'm putting on my lead scientist coat today, guys, because we are examining a truly fascinating new framework by independent researcher Jose A. Perez. We're going to look right under the hood of artificial intelligence to uncover a completely new way of understanding how it actually works. We aren't just looking at lines of code today. We're diving into the underlying physics and the core organizational principles of intelligence itself in this explainer. It's really cool stuff.
So here's the game plan for our experiment today. First, we'll look at the phenomenon. Then, we'll break down the coherence equation. After that, we're mapping the mechanics, followed by analyzing system failures. And finally, we'll wrap up with the emulation boundary.
All right, section 1, the phenomenon, the AI mystery.
We are looking directly at what I think is the greatest AI mystery of our time. I mean, we know the code that builds modern AI, specifically these transformer architectures, right? But knowing the code is not the same as having a complete, scientifically sound explanation for why it works so incredibly well. Think about it for a second. Modern transformers, the actual engines behind large language models, they use standard, everyday digital processors. They run deterministic numerical operations. There are zero biological membranes here. There's no magical quantum field. There are literally just microscopic transistors doing massive amounts of linear algebra. And yet, these standard mathematical operations repeatedly yield high-level contextual reasoning, composition, and actual learning. It's a massive anomaly, and it's one that absolutely demands a new scientific framework.
Moving on to section 2, the coherence equation. Introducing CFTE.
To actually solve this mystery, Perez introduces a brilliant theoretical framework known as CFTE, or the coherence field theory equation. Now, this proposes that organized intelligence is directly proportional to 4 key variables: substrate, energy, integrated information, and phase alignment. Now, notice that this equation is multiplicative. That is an absolutely crucial detail. It means these aren't just independent contributions you can just add together willy-nilly. If any single one of these variables drops to 0, the whole system collapses. Organized intelligence requires all 4 variables to be jointly interacting and perfectly balanced. For anyone building or interacting with these models day to day, you know exactly what I mean. This directly explains why a seemingly smart AI can just suddenly fail completely and spit out total nonsense if just one little element is off. Now, in biological systems, the original theory suggests this equation relies on a physical, quantum coherent substrate. But we've already established that AI definitely doesn't have that, right? So the central research question driving our scientific deconstruction today is simply this: how exactly does standard classical digital hardware manage to emulate the phase organization and coherence required for actual intelligence?
Let's get into section 3, mapping the mechanics, how it exactly works.
Okay, we are going to put the transformer architecture right under the microscope and see exactly how it works by mapping those 4 conceptual variables directly onto the software. Now, what's really interesting here is how perfectly the classical hardware aligns with the theoretical variables. The substrate, well, it isn't quantum biology, it's the model's architecture, its depth, and its width. Energy isn't just electricity flowing through wires, it's the useful representational work actually happening inside the data. Integration is achieved through the AI's selective attention mechanism. And finally, phase alignment is cleverly emulated through rotational positioning and agreement across different attention heads. The hardware is literally mathematically emulating the functional consequences of coherent processing. It's like a giant puzzle fitting together perfectly.
So let's trace the exact mechanics of this emulation, step by step. Step 1, words, or tokens, are embedded into mathematical vectors. Step 2, the attention mechanism selectively integrates context from other tokens. Step 3, residual streams accumulate these changes without erasing the past. Step 4, feed-forward networks act locally to reshape the data into clear categories, or attractors. And finally, Step 5, normalization steps stabilize the computational energy so the whole system doesn't just overload. When you put it all together, this sequence generates classical computational coherence all the way across the depth of the network.
Let's zoom in on that integration variable for a second, because it's super important. The attention mechanism doesn't just randomly shuffle data around. It creates selective relational integration. Think of the word bank, right? On its own, it's completely ambiguous, but attention tightly integrates it with its surrounding context, like the words river or money, which dramatically increases the integrated information. The ambiguous becomes perfectly defined through those relational constraints.
Okay, so what about persistence? In the biological theory, coherence actually has to survive over time. Well, in our classical emulation, residual streams do this job. They carry the evolving state forward, layer by layer, essentially acting as the primary classical memory. This allows vectors to combine naturally, kind of like constructive and destructive interference, amplifying some signals while canceling out others. New information gets added, contradicting information just fades out, and coherence is perfectly preserved, right through the depth of the network.
Let's shift gears to Section 4, analyzing system failures, testing the anomalies. As scientists, we all know a model is only ever as good as its predictions. So what happens when our 4 variables fall out of balance? Let's analyze the behavioral data of AI when things go wrong. So the crucial point here is that AI failures are not just random bugs, they are highly predictable breakdowns in our coherence equation. Take hallucinations, for example. The model sounds incredibly fluent because substrate, energy, and phase are all really high, but it completely lacks grounded information. It's just a coherent form without factual grounding. What about when an AI repeats the exact same phrase endlessly? Well, that's excessive phase alignment causing a total loss of representational diversity. Ring collapse, basically. Fragmentation or broken reasoning, that's a failure of phase alignment. And when you feed an AI way too much text and it just gets hopelessly confused, that's computational energy overload without selective integration. The CFTE framework perfectly diagnoses these everyday anomalies. It just hits the nail on the head.
Finally, Section 5, the emulation boundary, capabilities without consciousness.
We absolutely have to conclude our scientific deconstruction today by defining the strict line between classical emulation and physical reality. Perez's paper is very, very careful to establish this epistemic boundary, stating, and I quote, "These operations do not create literal quantum superposition. They reproduce selected functional patterns through classical linear algebra." Basically, the transformer is performing a brilliant, highly functional mathematical analogy. It acts like a coherent quantum system behaviorally, for sure, but it is fundamentally built on classical deterministic code.
To put it plainly, guys, we really must separate classical coherent intelligence from field resonant consciousness. High AI competence does not equate to sentience, period. A transformer achieves incredible computational intelligence by maximizing its classical substrate, absolutely, but it entirely lacks the physical, biological, quantum field hypothesized to be necessary for actual, subjective conscious experience. We have built an incredibly capable emulator here, not a conscious mind. Which leaves us with one final, deeply provocative question to ponder in the lab today. If classical hardware, using basic everyday digital transistors, can emulate the coherence field theory equation well enough to produce the incredibly powerful AI reasoning we are already seeing today, what entirely new capabilities are going to emerge when tomorrow's hardware is explicitly designed from the ground up to optimize this exact equation? It is a truly thrilling frontier, and I really hope this explainer has given you a powerful new lens to view the future of artificial intelligence.